Hello, welcome to another problem session. So today we have a really interesting problem. The problem says that there's a ring. This is the ring which is rotating at this angular speed, and it has a radius r. And there is a little bead that slides on this ring. But if you place the bead here, and it's rotating at that speed, so the bead just goes around with the ring in this circle and doesn't go anywhere. It stops sliding back and forth. So we're supposed to find this angle. Okay, so here is the answer. Here is the answer that you should get. So if you want to try it out and come back and check my answer, my solution, that's okay. So how would we look at it? Okay, we can look at it from inertial perspective. So inertial frame, so let's see, this is z-axis, and this is x-axis, and this y-axis is, and so this is a fixed axis. It's not rotating, and ring is rotating with respect to that. At some instance, the vertical angle with respect to the z-axis is theta. So if you look at the ring, I mean the bead itself is going in this circle of this radius of this circle in which bead is going. So like a circular motion for the bead, right? It's r sine theta. So we can write out circular motion for the bead. I can completely forget about what the ring is doing. Okay. So strategy is write F equals ma for the bead. It's a uniform circular motion. It's uniform since omega is fixed. Yeah. Okay. So in that case, you can see that acceleration of the acceleration will be towards this circle in which it's going. Center of the circle is here. So at this instant, it will be v square over this radius r in which it's going. Not capital R, but small r, right? And what is v? Well, it's rotating with omega, but it's going in this radius r. So v is just omega little r square over r. So this is AC is omega square r. So at this instant t, let's look at which way the forces are, because we already figured this one out. We also know the direction. So let's see, the whole thing is in the YZ plane. So we don't worry about the x-axis forces. In this, at this instant, you can see that we have a, let's take a, so this gravity is still way down, this mg, and the normal is pointed in that direction, perpendicular to the tangent. This is the tangent. So normal has to be pointed 90 degrees to this tangent. Its normal is coming from the ring. So there are only two forces, weight and the normal from the ring. So we are in the YZ plane. So this equation becomes Fy, which is the direction which the acceleration is, Fy equals to MAY and Fz equals MAZ, and AZ is 0 because all the acceleration at this point is pointed towards negative y-axis. So this is m negative omega square r, and this side is, this is equal to m times 0. So we can write what Fz is, we can write what Fy is. So let's look at how can, so here is another diagram. So this angle is theta, so this is theta. So you can see that from here, this is the same angle as this. I mean, this angle is same as that angle, which is the same as that angle, this theta, and the n is that way. So this is same as this theta. So this is the z-axis and this is the y-axis. So for mg is all mz has no y component. So this is all from the normal, and the normal is a negative y component, n, and this is going to be sine theta. And this one will be negative mg and positive n cosine theta. So let me pause here. Okay, so now we have all the components here. So from here I get n cosine theta equals mg. From here I get n sine theta equals to m omega square r. And you can see already that little r is capital R sine theta, right? So this is m omega square capital R sine theta. So we can see this cancel out, and I can put n here. That gives me cosine theta, m omega square r is mg, and m cancels out, and hence cosine theta equal g over omega square r. This will tell me theta equal to r cosine g over omega square r. That's it. This is an interesting simple problem. I will talk to you in another video. Bye.